And welcome to another Math 1206 Q&A. What are you doing here in my apartment? I thought we were supposed to be doing that whole social distance thing. Well, yes. Things are getting serious out there, and as of yesterday, my movements are now more extremely limited. I have to actually obey the self-quarantine thing, not because I actually got sick or anything. That's not what I'm saying. But things are closing down more forcefully, let's say, and I'm unable to actually get access to classrooms that I could have gotten access to before today. So I'm doing the whole hashtag stay at home, hashtag flatten the curve, hashtag math must go on thing. And I am coming to you live out of my living room. And it's not an April Fool's joke. This is probably what it's going to be like for the rest of the semester. And so we should probably just get used to it and move on. Things have been rough, and I saw a meme earlier today where it was like the essential employees. It was like a SpongeBob meme, and it's like, they're stuck between a rock and a hard place, and it's kind of like on one hand, they're happy to have a job that they're still getting paid for and all that good stuff. But on the other hand, they're not like everyone else who's like working from home. And so they actually have to go out and continue to do work. That's how I feel. I feel like, I'm sure there are other things like this, of course, especially in like the healthcare field, but I feel like as a teacher, your life gets a lot harder. Like my life has gotten a lot harder teaching long distance versus close range. So much more preparation, so much more stress. My migraines are back on the daily now. And of course, I know first world problems, and a lot of people have a lot bigger problems now than me, but just so you know, that's what's going on. The only benefit of this, really, as far as I can see, is now I don't have to put on pants to go to work, right? So, kidding, April Fools, I am wearing pants. There it is. Which, it's out of respect for you guys. So don't worry. I could have not been wearing pants, but I actually am. That being said, we are just going to get into it. Taught a few lectures today already, uploaded them already, and I think you guys are the last one for today / tonight. So hopefully this is going to go by smoothly. The other stuff wasn't perfect, but for the most part, the technology kept up, and let's keep that good streak going. So in the meantime, I'm going to share something with you, which is pretty much how I'm going to continue this lecture and future lectures. So I got something to write with from home, which, I can't have a blackboard or a whiteboard. I hate whiteboards to begin with. Now I have like a digital whiteboard, but we're going to make the best of it. Let me share my notes with you. So now you should be able to see the notes book page. So I'm going to be using OneNote, and I'm going to be able to write in this notebook, but I have things just a little bit pre-prepped here. Copied questions from the questions from Jupiter grades that I've been getting. And yeah, so for Math 1206, as you know, you are watching pre-recorded lectures, and I will post Q&As answering all your questions. And hopefully by the time I answer all your questions, you will be right as rain. There is something that I do want to try though, because I keep looking at myself in the corner, which causes me to look away from the camera. And it's always like, what is Jhevon looking at? But if I move the video in the middle, I'm not sure if it blocks your view or just my view, and that might be an issue. Anyway, without further ado, let's get through it, because I am about ready to wrap the day up. I've been working all day. So let's get into it. So these are some Q&As. I copied and pasted them from Jupiter Grades. We're going to take these one at a time. I believe there's a couple questions being overlapped here, but let's move on with the first one. Yeah, that did not want to do that. Let's move these guys. Okay, so here are the questions we're going to answer, and I think there's some of these that might take a little while. Some of them are going to be shorter, but we will make the best of it. Let me just move some things out of the way here. I don't know. Is the first question that long? I don't know. Okay, let's jump into it. We're going to continue with the Q&A business. Let me change my screen settings here so I can see easier. Okay, all right, let's do this. So, good afternoon. I understand what lecture 26 was about. That was one where we were finding critical points and graphing stuff. And I had one small clarification. At around 4630, there's no max or min value because 0 didn't have a solution. I believe what you want to say is that the function was undefined at 0, and you would be correct. That is why it was not the case that that was a maximum. Just to refresh your memory here, where's my pointer here? Okay, we were looking at the function f of x equals 1 over x squared, which I know we all know how to graph that, but I was going through the motions of doing a curve sketching example where we graphed that. Some of that you know what the picture would look like. It involved us finding a critical point, the critical points, and testing them, which involves you finding the first derivative, which in this case would be 2 over x cubed. It also involved you needing to find the second derivative, which I'll talk about in a bit, which would have been 6 over x to the 4th. Right? So this guy you think of as x to the minus 2, you bring the minus 2 down, subtract 1 from the power, you get minus 2x to the minus 3, which is the first derivative. Then you bring the minus 3 down. When you're differentiating, you get positive 6x to the minus 4, which is 6 over x to the 4. Anyway, okay, so there came a point where we're actually doing the first derivative test, and I believe there were questions about this, so I'll actually run through an example here. So there came a point in the curve sketching. What step is this? I believe it was in step 4 of the curve sketching process where we do the first derivative test. Now, theoretically, I described this already in the lecture, so I'm not going to go through the theory of how it's done. I'm just going to go through an example, and hopefully by me going through a couple of examples, it will clear up some misunderstandings moving forward, because obviously the way I said it in the lecture didn't land for some people. So I think just seeing a few examples of us going through this will be okay. So remember what the first derivative test is. First, it means you're going to be doing tests in the first derivative. So it's the first derivative test. It's called that test for a reason. So the first thing you want to do is you want to find the critical points. Okay, so this is where your f prime equals 0 or undefined. And you could have a function where you could have a critical points at both or either or one or the other or neither of these situations. I believe that was a question someone asked me the other day, even though they didn't ask me in Jupyter. What you would do in this case is you would means 1 over, sorry. So what we would test in this situation is we would set minus 2 over x cubed to equal 0 or undefined. Now, it's never actually 0 because it's a fraction where the numerator is never 0. So this situation does not apply here. That's not going to be true, but it is undefined when x is 0. So it means that that guy here, this is harder than it looks. Like I've been trying to be able to draw a box, like box my answers all day in all the previously recorded lectures, and it just did not work out. So that means x equals 0. This here is the only critical point. I lost where my pointer is. Okay. This means that this is a critical point. And so now we are in the situation where we want to apply the first derivative test. Now here's the test. Once you find the critical points, you are going to essentially draw a number line. I think visualizing it that way is one of the best ways to do it. And you can write a little f prime on it, and just to remind yourself that you're plugging things into the first derivative, and you plot your critical points there. Now what you do is to the left and to the right, in between all the critical points, there's only one to consider here. You plug in a random number. So let me plug in, say, -1 on this side, +1 on that side. And what you're going to do is, this down a little bit. What you're going to do is you're going to take these numbers and you're going to plug into the first derivative, and you're going to see what sign results. Now, if I take x equals -1, plug into the first derivative, -2 divided by -1 cubed is actually a positive number. So here we would have a positive sign, which in the first derivative means, that's right, it means the function is increasing. Now, if you plug in +1 into x here, we have a negative sign, which means the function is decreasing. So now we get to the question, which, let me move this video, like on my screen, the video is in the way here. So let's get to the question. So it said there's no max or min because the 0 didn't have a solution. So technically, we looked at situations like this before when you're increasing on the left and decreasing on the right. That would normally indicate a maximum point. However, for it to be a maximum point, that point actually has to be defined. It has to, your function has to be continuous there. So 0, f, the original function, which is 1/x², is not continuous at x equals 0. So this point is nothing, right? So it's not a max or anything. It is a critical point, but it's not some feature on the graph. In fact, the graph does not exist there. So in answer to the question, yes, it looks like from when doing the first derivative test, someone asked about the second derivative test and it's late, whatever. When you're doing the first derivative test, you will see patterns that might look like a max or min, but you have to make sure that at the point the function is defined so that we will know that it's a max or min point on the graph. If the function is not defined at the point, then it's nothing. It's going to be like a hole or an asymptote. And in this case, it was an asymptote. So yeah, that's why it wasn't a max or min. Hopefully that answers your question. There were more questions about the first derivative test, I think. And so we'll get back to it. But this basically here, everything I did here was the first derivative test. So you would find the derivative, find the critical points, then you plot them on a number line, test numbers in between the critical points in the first derivative, see if you get a positive or negative. This indicates increasing or decreasing. Now from this, the whole point of doing all of this is you will be able to talk about where is the function increasing, where is the function decreasing. You'll also be able to talk about maximums. You'll also be able to talk about minimums. Okay, so here you would notice that the function is increasing from -infinity all the way up to 0, not including 0. It's decreasing from 0 to infinity. Your maximum, you have none, and your minimum, you have none. So this will be the whole point of doing the first derivative test, is to be able to get this piece of information here. See, this is what I'm talking about, me trying to draw boxes all day. Like, that's one of the best boxes I've drawn all day, believe it or not. Okay, so the whole point of the first derivative test is to get this particular kind of information. Where's the function increasing? Where is it decreasing? Are there maximums? Are there minimums? And you do it by doing this chart where you draw the first derivative and you test the signs of the derivative in between the critical points. And of course, you have to know that the critical points occur when the derivative is 0 or undefined. So hopefully that answers your question. Yes, 0 was not a maximum in this problem because 0 was not a point that existed on our graph. At x equals 0 did not have a corresponding point on our graph. A follow-up, also unrelated general question about the lecture. We now have recitation on Tuesdays, correct? Okay, so this was from a student that is in my Calc 1 class that normally has recitations on Fridays. Now, when it comes to recitation, what happens is the recitation instructor for my class that does it on Tuesdays, he is holding interactive recitation sessions via Zoom, whereas the recitation instructor that deals with recitations on Fridays does not have the equipment to be able to do this, so they are not. So what I told my classes were, so in answer to the second question, maybe I can do this to answer the second question. Type. Don't even know how to type anymore. Second question. Zoom recitation where you can discuss mock quizzes that I post will be on Tuesdays. Okay, so it's not that your recitation was moved to Tuesdays, technically speaking. It's just that that's when I can know that you can have an interactive experience with somebody. And so that's why I indicated, okay, so on Tuesdays, if you want to be able to bounce ideas off somebody, which is a good idea with this long distance learning, Tuesdays would be the day that you'd want to do it if you're not seeing me during my office hours on Zoom. So yeah, that's what that was about. So yes, also something else that was mentioned here, are we actually going to take the quizzes? So you should take the mock quizzes prior to the Zoom sessions and discuss results / solutions with the recitation instructor. You do not need to submit the quizzes. They are for you to be able to test yourself. So it behooves you to take the quizzes honestly and fairly. Set a timer, do the quizzes, see what you get, see where you understand, see if you would have gotten the point had the quiz been graded. You don't need to scan it and send it in to me. It's not going to be graded. It is mock quiz. It is all the quizzes from now on are going to be mock quizzes. It's pretty much me just kind of trying to get you to know what you know from what you don't know. Because I know even though I beg you guys and I ask you guys to watch the videos, engage with the material, ask me questions, a lot of people aren't going to do that. So one way for you to know that you understand something, because a lot of people would watch a video and they'll feel like they understand, but they really don't, because you're not going to understand unless you do something on your own. So I give you guys mock quizzes so that you can kind of test yourself and kind of know what you understand from what you don't. It will also help you to ask me more questions if I need to clarify anything. So Zoom lectures for recitation are on Tuesdays, and I believe an email was sent out to you guys regarding the timing and all that good stuff. My class that usually has recitation on Fridays, you are welcome to join. And that's why I asked the recitation instructor to send emails to both my 1206 classes. And that's just because the person who does recitations on Fridays just does not have the equipment to actually accommodate such a request. So I think it's a good idea for you to discuss your answers with somebody. And yeah, recitation, which would be when you would do it anyway, is as good a place as any. So that is the situation. So hopefully that answers the second question. So pay attention to that. Yeah. All right, let's move on to the next question. Maybe I should put the questions in bold or something. Bold, that's a question. Here's a question. Bold. This was just a note to myself to remind me of what the scene was talking about. Can delete that. So we're having a recitation and quiz on the Tuesday section. Okay, so I just answered that. So if you want an interactive experience, yes, you have to log on Tuesdays to talk to the recitation instructor. If you're fine without it, which I don't recommend, then you don't have to attend, but highly recommended that you attend. And you will, of course, we are, of course, keeping track of who does attend. So, you know, we can kind of see who's been at least trying to attend. But I do understand that under the circumstances, not everyone, it won't be possible for everyone to attend. And in that situation, I would much rather you actually reach out to me and tell me, hey, Jhevon, I'm having trouble attending the recitation sessions for this reason, and we'll try to work something out. But in general, it is to your benefit to attend the recitation on Tuesdays, and I'll track attendance as well. How do you want us to upload the quizzes? I don't. So it's for you, for your benefit only. So yeah, this one, yeah, answered above. All right, so we're done with that question. Thought I heard something. There, we are done with that question. Okay, move on. This is fun. 2 more questions. Third question. Bold. Good afternoon. From lecture 25, you bring up the first derivative test. I didn't really understand it. Could you maybe do an example or re-explain it? So I did an example above, and I did another example in class. So maybe I can do another example. What was the example that I did in class? Forgot. And let me make sure that I'm not actually repeating the same example. Oh, well, lecture 25, at that point, I didn't really do examples yet. So maybe after watching lecture 26, which at this point, everyone should have watched it, that question would actually be clear. All right. Okay, so I think I see what example I did. So I also did another example in lecture 27. So there are other examples. In lectures 26 and 27, which this person had their question from lecture 25, so I'm not sure if they saw these, but here's another. So suppose I have a function 4x over x squared plus 1. So now the first derivative test, right, which in the curve sketching situation is going to be around step 4. What would the first derivative test look like? So remember, this is where you first find where the derivative is 0 or undefined. You plot it on a number line. Now, the derivative was given on the example, like I'm using the curve sketching handout to pick the other example here. And I just touched my face, bad Jhevon. Okay, so f prime was given here. This is 4 times 1 minus x squared over x squared plus 1 squared. Right, so this means here, when you're trying to apply the first derivative test, the first thing you're going to want to know is where is 4 times 1 minus x squared over 1 plus x squared equals 0 or undefined. Now, of course, it's never undefined, but it is 0 if x equals plus or minus 1. And so what you would do is you would actually test that. You would actually draw a number line, and you'd plug in -1 and 1. Then you plug in points in between these guys. So you would plug in, so, and it doesn't matter what you pick as long as you pick something on the other side. So -2 could work, a 0 could work in between them, and a 2 could work on the outside. And I'm plugging these guys into the first derivative, which is this guy right here. That's f prime. So testing f prime, it's called the first derivative test. So if I plug in a -2 here, one thing you can notice, the 1 plus x squared in the denominator should be 1 plus x squared squared. 1 plus x squared in the denominator is always going to be positive. So really just the numerator can tell me what the sign is. If I plug in 2 into x in the numerator, I get 1 minus 4, which is negative. So on this part here, it's negative, which means decreasing. If I plug in a 0, I get a 1 minus 0, which is positive. So it's increasing. And if I plug in a 2, it's negative. So it's decreasing. Now, unlike in the first situation, the function is defined here, right? So the denominator is always positive, so it's never 0. So this is actually a min here. And this is actually a max here. And you can plug them in. If you use the original formula, find f of 1, that's going to be the corresponding y value, f of -1. You're going to plug that into the original. So you would get -4 over 2, which is -2. And for this guy, you would plug in, find the corresponding y, which is f of 1, and you get 4 over 2, which is 2. So that tells me the coordinate -1, -2 is going to be a minimum, and 1, 2 is going to be a maximum. So that is the first derivative test. So from this, you can actually make a conclusion here. So from this, you can make the conclusion of where is the function increasing? Where is the function decreasing? Where are their maximums? Where are their minimums? So from this, we can see that it's increasing on the interval -1 to 1. We see that it's decreasing from -infinity to -1, union also from 1 to infinity. We see that a maximum occurs at 1, 2, and we see that a minimum occurs at -1, -2. And this here, this is a lot harder than it looks, believe me. Okay, and yeah, that would be the first derivative test. So again, whenever you do a process like this is called the first derivative test. Find the critical points of the first derivative, plot them on a number line, plug in numbers in between them in the first derivative. You will get a sign. You only care about the sign. You don't even care about the value more specifically. You care about the charge, the sign charge. So negatives and positive. Negatives mean decreasing, positive means increasing. And if you have something that is, well, from your point of view, decreasing then increasing, that's a minimum, provided that the point here actually exists on the function. If it's increasing then decreasing, that's a maximum, provided that the point on top is actually in the function. And in this case, they were. So that's the first derivative test. You're just actually testing for increasing, decreasing, maximums, and minimums. Hopefully that second example gave you a better understanding of the first derivative test. And here is another question, again from lecture 25. So let's bold that, that's the question. Okay. I'm a bit confused in lecture 25 about the notation. Is there any specific one you want us to use, or are they all interchangeable? So I believe this was notation for the derivative that were being referenced, was being referenced here. So there's the prime notation, meaning you can write f prime of x or y prime, or you can write f double prime or y prime, double prime, etc. And then there was the Leibniz notation, where you write dy dx to represent the derivative, or you can write d squared y dx squared and all that stuff. And I gave you the sign chart, the notation chart, etc. Yes, you can use either notation. Now, as a personal preference, I'll mostly use the prime notation, as you'll see in the lectures. But the important thing is you can use either or, just don't mix and match. So if you're using the prime notation, stick with the prime notation. Use the prime notation everywhere in the problem that you're doing. Don't mix notations together. So just choose, do you want to use the Leibniz notations or the prime notation? Now, there are cases in which I would prefer to use the Leibniz over the prime notation, and situations like related rates would be a situation where I would prefer the Leibniz notation to the prime notation, or any situation in which identifying the independent variable is going to be an important thing, I would tend to use the Leibniz notation. Otherwise, I would use the prime notation whenever the independent variable is understood, and it's just not really important to identify who the independent variable is. So because the prime is just easier to write down, it's easier to write down a stroke as opposed to dy over dx or dy dx, I'll tend to use the prime notation, but you can use either one. Just make a choice, commit. If you're going to use the prime, use the prime. If you're going to use the Leibniz, use the Leibniz. Just make sure that you don't mix them together, and just make sure that you don't get mixed up by using either notation. So with the prime notation, there's always a risk that you will misidentify your independent variable in certain situations, which in Calculus 1, pretty much the only place where I see this being an issue is with related rates. I don't really see it being an issue otherwise in Calculus 1. In classes above this, there will be more situations, but also in classes above this, the students tend to be more mathematically mature, so they'll probably not make the mistake anyway, but there's a risk. Another question I have is, If a function is both increasing or decreasing an interval, would we restrict the interval specifically discuss the instance of increasing, decreasing? Okay, so you can't have it increasing and decreasing at the same time unless it's a constant horizontal function. But yes, let's say you had this wide interval where we had both behaviors of increasing, decreasing. Yes, you would separate the intervals, just as I did here. I mentioned it's increasing over here, it's decreasing over here. You would separate them in that case. I don't know if that was your question, but hopefully that answers it. So yeah, how you would go about this first derivative test. So exactly I showed you above here is how you'd go about it. Another question I got, which isn't here. So another question was about the difference between the first derivative test versus second derivative test. Or I think the student asked me versus the concavity test. So first derivative test, we actually did this. Did above. The second derivative test is actually gives info that you would get from first derivative test. So essentially useless for us. You'll never actually have to use the second derivative test in this class because this identifies maximums. So if your second derivative is continuous, this tells you when your second derivative is positive. That means concave up. It identifies a minimum. And if your second derivative is negative, it identifies a maximum. So it's another way to do max and min. However, you need that f double prime continuous for you to make the conclusion at the point. So it only tells you about max and min. The first derivative test will tell you about maximums, minimums, also tells you increasing, decreasing. You get more information from the first derivative test than the second derivative test. And for the purposes of this class, any question I ask you, you'll have to do the first derivative test anyway. So the second derivative test is kind of useless at the end of the day. The concavity test also uses the second derivative, but it's a whole different ballgame. This uses the second derivative test, not the second derivative test. It uses the second derivative, but you plot things on a number line just as you would with the first derivative test. And in this case, if you see a plus sign, it tells you about concave up, right? So concave up. And if you see a negative sign, it tells you about concave down. So this is pretty much step 5 in the curve sketching examples that I mentioned. So this one talks about concavity. Talks about concavity and inflection points. Right? So these tests are all used for something different. So your first derivative test tells you about increasing, decreasing, maximums, minimums. Your second derivative test only tells you about maximums and minimums, and you have to have a continuous derivative for it to even tell you that. Whereas the first derivative test doesn't have that requirement. The concavity test is to identify inflection points and where you're concave up and concave down. And so don't mix these guys up. So the second derivative test and the concavity test, they both use the second derivative, but they actually have a very different purpose. And so don't mix those up. Just because they both use the second derivative doesn't mean they're actually after the same thing. It's actually the first and second derivative tests do the same thing. And like I said, second derivative test is essentially useless. So what you want to just pay attention to actually, the screen. The first derivative test and the concavity test are the important tests for you to know. And when it comes to curve sketching, drawing these things are actually pretty hard. When it comes to curves, so this you want to know, this you want to know, this can ignore. But yeah, so the first derivative test is as I described before. The concavity test, the process is essentially like the first derivative test, except you're using the second derivative. And your plus and minus signs mean something different based on the interpretations that I mentioned before. Positive in the second derivative means concave up, negative means concave down, like a frown. I believe that was all the questions. Definitely that was all the questions that I have here. And what were, these were emailed to me, and I believe the question I just mentioned off the top of my head, I believe it was either someone asked me in office hours or they just sent me an email not through Jupyter. And yeah, so that's the answer. Another question, and this was through office hours. Someone was asking about the theorems. Do we need to know the theorems? So in the lectures that you guys have been watching recently, I covered things like the extreme value theorem. We covered Rolle's theorem. We covered the mean value theorem. A while ago, we covered the intermediate value theorem. Etc. So that was the question. How deeply do we have to know these theorems? How deeply do we have to understand them? I proved all of them except the extreme value theorem. Another one that I proved was Fermat's theorem, etc. So the answer in short is answer. You need to know the statement of the theorems and know how to apply them. You do not need to know the proofs of the theorems. Examples of when and how to apply them have been done in the lectures. You would have also seen them in the homework. Right, so you should know what the mean value theorem says and know how to use it. So if I ask you a problem, it's a very fair problem for me to say, here's a function f of x, here is an interval, find the c guaranteed by the mean value theorem. And that is the question. And you need to know the statement of the theorem to be able to find the c. Or I might say something like, can we use the mean value theorem here? And you should know what conditions are necessary for you to be able to use the mean value theorem. So your function f of x must be continuous on a closed interval ab and must be differentiable on the open interval ab, and that's it. Once you have those conditions, you can apply the mean value theorem. And that just basically says there is a point in the open interval AB, a point C, such that the derivative at C is the average rate of change. So f prime of C is equal to f of B minus f of A over B minus A. That's the mean value theorem. You should know the statement. You don't need to know the proof of it. But you should know the statement, you should know how to apply it. And that goes the same with all these other theorems. Extreme value theorem, you're not gonna really apply that directly anywhere, but you should still know it, because I've seen in the past where I asked absolute max and min questions. The extreme value theorem that's the theorem that says continuous functions on a closed interval are guaranteed to have an absolute max and absolute min. And there have been times in tests where I give students a continuous function on a closed interval, ask them to find the absolute max and min, and I've gotten responses to the effect of saying, oh, this function has no absolute max, or this function has no absolute min. And I'm like, if you came up with that answer, it means you don't know the intermediate value theorem. That's impossible. They have to have an absolute max or min in this situation. So you need to know the theorems, because otherwise you'll come to the wrong conclusions, and there are problem types that you won't be able to solve unless you know the theorems, know the statements. You need to know what conditions need to be met. So extreme value theorem just means you need a continuous function on a closed interval. And the theorem says, in that case, you're guaranteed to find an absolute max and absolute min. Rolle's theorem, basically, you need to be continuous on the closed interval, differentiable on the open interval, and f of A must be equal to f of B, right? So your endpoints have the same values. Then Rolle's theorem says there's a point in the middle such that f prime of C is equal to 0. The mean value theorem generalizes this, and it says under those conditions, even if the endpoints aren't the same, there's a point in the middle where the slope, the instantaneous rate of change, is the average rate of change. Intermediate value theorem is basically saying if your f is continuous and your f of A is less than some number, less than f of B, then there must be a number in between A and B such that it hits that number in the middle. Continuous functions attain all intermediate values. And Fermat's theorem, that was the one that says if you have a maximum or minimum, if you have an extreme point, in other words, then, and the derivative exists, then the derivative must be 0. And that was a big factor in us defining critical points the way that we did, which, by the way, I believe someone also asked me about critical points versus critical numbers. For us, you can use them as one and the same. Technically, when we say critical number, we're talking about the x value. When we say critical point, we're talking about the coordinate. But these guys are often used interchangeably when verbally talking about them. Okay, that I think is it. Those are all the Q&A. Hopefully that cleared up some of the situations that were unclear in the lectures. I believe you guys should be up to lecture 27, 28 now. So send in your questions for, I believe lecture 27 was covered. Yeah, so send in your questions for lectures 27 and 28, and I will get back to you on those on Friday, pretty much in the same format. Hopefully you found this format helpful. Hopefully I answered some of your questions. But yeah, that's basically it. I will provide, hopefully it's helpful, these notes in PDF format, but you'll probably want to also be taking your own notes. That will be most helpful. And as I said here, quizzes from now on are mock quizzes. They are not going to be graded. If you want feedback, which I highly recommend that you do get feedback in real time, do the quizzes whenever we get quizzes and log on to the Zoom lecture to go through them with the recitation instructor. Know the first derivative test, know the second derivative. You don't even need to know the second derivative test, really. Know the concavity test, and know when to apply them, what they tell you. The curve sketching handout kind of tells you when to apply them. It would say, yeah, step 4 in the curve sketching handout. It tells you what you want to find, and it tells you that the first derivative test will help you with this. And in step 5, it tells you what you want to find, and it tells you that the concavity test helps you with this. So if you want to know when are these tests useful, the curve sketching handout actually tells you when they're useful and what they do. And in class, I did examples of us applying these. I think that's it. I think I've answered all the questions, and it's about time to go to bed. So hopefully that was helpful. I will see you guys in the next one. And yeah, so this is Jhevon about signing off. Yeah, hashtag flatten the curve, hashtag work from home, hashtag calculus or bus, hashtag keep watching lectures, keep being engaged, try to engage as much as possible, pause videos, try problems on your own, ask me questions whenever you ask them. I will be holding office hours through Zoom. Recitation is on Tuesdays through Zoom. Yeah, keep the questions coming and stay safe. And with that, I am going to sign off and ciao.